So continuing on with our example of the integral test, what I did was I took this infinite series and I just wrote it as this improper integral. So what we should start with is evaluating the improper integral, and based on whether we get a divergent or a convergent improper integral, we'll be able to make a determination about whether our infinite series converges or diverges. But the first thing that I actually want to look at is the checklist of our ability to use the integral test. So remember, in order to use the integral test, our function e to the negative k, or if you'd like 1 over e to the k, it has to be positive, it has to be decreasing, it has to be continuous. Okay? So if you think about what the graph of 1 over e to the k might look like, and you can of course use your graphing calculator just to double check as you begin to work on some of these. After a while you should be able to make that prediction without having to graph the function on your calculator. But let's take a look. So here is my graph of 1 over e to the x, and you can see that the entire graph is lying above the x-axis. It is continuous and it is decreasing. So in terms of our checklist, it kind of meets all of our criteria, and also we are going to assume that f of k is equal to a sub k, which is the formula in our infinite series. Okay, so moving on, since it does meet all of our criteria, then we're going to proceed in using the integral test. And what I'm going to do is I'm going to evaluate the improper integral. What you'll see happen a lot of times in the homework is that they're likely to write these with x's as opposed to k's, but since it's a variable, it makes no difference whatsoever. So in order to evaluate this improper integral, I'm going to write it as the limit as b approaches infinity of the definite integral from 2 to b of e to the negative x dx. I'm going to evaluate the antiderivative, and I'm going to plug in the limits of integration from 2 to b. So the antiderivative of e to the negative x is negative e to the negative x. Let's go ahead and plug in b and 2. So I'll have negative e to the negative b minus a negative e to the negative 2, so it becomes plus e to the negative 2. Might be helpful to look at these without the negative exponents as you're evaluating them. So negative 1 over e to the b plus 1 over e squared. And I want to see what the limit is as b approaches infinity. So here, as b approaches infinity, my denominator goes to infinity, which means that the entire term here will go to 0. And then since this one doesn't have a variable term, that is my limit. So the fact that we were able to come up with a constant for our limit means that the integral converges. Okay, so the integral here converges to 1 over e squared. But what we were asked to do is to evaluate this infinite series, and we use the improper integral in order to do that. So let's make our official conclusion, our final conclusion, based on what the problem asked. And the conclusion is that this particular infinite series converges. And it converges because the improper integral, using the same function defined in the series, also converges. However, we don't know if it converges to 1 over e squared, and we don't care. We're not asked to state that. We do know what the improper integral converges to, but we don't know what the series will converge to. We just know that it does converge. Okay, so that is how the integral test works. Let me just run through the overall concept with you once more. First thing you'll want to do is make sure that it's usable based on the function that you are working with, positive, decreasing, continuous. If that's the case, you're going to set up an improper integral, and you're going to evaluate that and determine whether or not it converges or diverges, and then you're going to make a conclusion about the infinite series from there. Let's do another example. This one is a little bit harder only because the integration is going to be a little bit more complex. So same directions, different series, k equals 1 to infinity, k e to the negative 2k squared. Okay, so first thing that I want to do is decide, does it meet the checklist? So let's take a look at the graph. X e to the negative 2x squared power. Okay, so I need to zoom in a little bit. Let me adjust my window and see if that gives me a better picture. Okay, maybe even more. Let's go negative 2 to 2, negative 2 to 2. Okay, so you can see that the function is not entirely positive. There are sections of the function that are below the x-axis. You can also see that there are sections of the function that are increasing as opposed to strictly decreasing. It is continuous all over, so we don't have to worry about that. But the one thing that you want to remember here is that when we talk about whether it's continuous, whether it's decreasing, whether it's positive, we want to look at all of these things over the limits of our series. So we want to look at them for k greater than or equal to 1, because those are the values that we are actually plugging in to create this infinite series. So when I look at this graph, I want to probably change my window, maybe from 1 to 10 or something like that. That's too much. It stops there. Sorry, let's try from 1 to 2. Okay. Let's adjust the y-axis a little bit. Whoops. Yikes. Making this worse. Okay. Good enough. So here's my graph from 1 on, and you can see that it is in fact decreasing. It is in fact above the x-axis, and we said continuity wasn't an issue to begin with. So we can put a big check mark here for the values that we're interested in. Our function meets our criteria. So let's go ahead and set up this improper integral from 1 to infinity. And if you'd like to use x's instead, it's kind of strange how that actually helps. For some reason, writing these dk's just seems weird. So So I've found for myself that changing it to x's does actually help. So what I'd like to do now is I'd like to give you a chance to see if you can just evaluate this, and then we will together make a conclusion about what that means in terms of the infinite series. This test can't be inconclusive. If it fits our criteria and we are able to integrate, then we have an answer. We know that it either converges or diverges. So the problem is, can you integrate this? And you absolutely should be able to integrate this. And hopefully you're already thinking of using integration by parts. Okay, so I've already worked through it. Why don't you pause here and see if you can make a determination about whether or not this integral converges or diverges, and then you can come back and check your work. So in terms of integrating this, I did try integration by parts, and it wasn't successful, but substitution was, which I probably should have tried first anyway. So in terms of substitution, if we let u equal that exponent, negative 2x squared, then du is negative 4x dx, and we can compensate for that for that negative 4 that we don't want by dividing both sides by negative 4. From there, let's make the substitution. So we've got e to the u, and then, oops, I forgot my x in here, which is important because x dx is equivalent to negative 1/4 du, but then of course that negative 1/4 can be pulled out in front so that we're really just integrating e to the u du. That's really easy to integrate. We get negative 1/4 e to the u, and then let's resubstitute negative 2x squared. So that's what we get when we just evaluate this piece here without any regards to our limits of integration. Let's go ahead and think about that as well. Well, first of all, I need to get rid of that infinity from my limit of integration. So I'm going to use a b instead. And I'm going to find the limit of that integral as b goes to infinity from 1 to b. Well, since we already found the antiderivative, we can say that we're taking the limit of negative 1/4 e to the negative 2x squared from 1 to b. Let's plug in our limits of integration and evaluate the limit. Okay, so if I plug in a b here, I'll get negative 1/4 e to the negative 2b squared. And if I plug in a 1, I'm going to get minus 1/4 e to the negative 2. Let's let b go to infinity. What's going to happen to this entire exponent here is that it's going to become negative infinity. So this whole thing is really like having negative 1 over 4e to the infinity power. And that whole thing is going to go to infinity on the bottom, which means the term goes to 0. And so my final result is negative 1/4 e to the negative 2. I just realized I had made a sign error here. When I was plugging in my limits of integration here, I need to minus a negative, making that a plus. So anyway, 1 over 4e squared is the answer to the limit, which means that that improper interval converges. And so our final conclusion is that our infinite series, k1 to infinity, also converges. We don't know what it converges to,